Okay, so we're starting back. But before we go on to means, I want to kind of address something I had just mentioned. So I said in example 13, right? Prove that if x is a positive real number, then this is true. And that is true. But I said you have to be careful because if the condition was x is a positive real number greater than or equal to 2, then this would not be true, right? So, okay, it's not that it would not be true. It would be true, but this 2 wouldn't be the minimum value that you would get. So the question was actually saying, find the minimum value of this expression when x was greater than or equal to 2, then the answer would not be 2. The answer would be 5 over 2 or 2.5. Right? And how you would do that is, there are a couple ways to do it. One way would be to prove that x plus 1 over x is an increasing function for x greater than or equal to 1. Actually, it's increasing for x greater than, let's see, 1 over x cubed. Anyway, x is greater than or equal to 2. So for that range, x plus 1 over x is an increasing function. The problem is it's not easy to show that this is an increasing function without using differential calculus, meaning without differentiating and finding second derivative and those things. So the other way to do it would be, or the easier way to do it would be actually forget about increasing function, just consider this. Right? We know x plus 1 over x can be written as this, right? Now we know when the only restriction is if x is a positive real number, then it would be minimum when this thing is 0. The problem now becomes, well, if x is greater than or equal to 2, this thing could never be 0. So the minimum isn't actually 2. But what we note that is if x is greater than or equal to 2, or let me use a different number because I have 2 here. Let me say x is greater than or equal to 3. So if x is greater than or equal to 3, then basically what I have is x minus, look at the thing inside the square root. Square root of x would be greater than or equal to square root of 3, right? Now, if square root of x is greater than or equal to square root of 3, then 1 over square root of x, because it's positive, would be less than or equal to 1 over square root of 3. And then when I multiply by a negative sign, the sign reverses. So I would get minus 1 over square root of x is greater than or equal to minus 1 over square root of 3. Now, what that basically tells me is that this expression inside here is greater than or equal to square root of 3 minus 1 over square root of 3. Right? And that thing is always positive. Right? Square root of 3 minus 1 over square root of 3. Once x is greater than 1, this is always positive. So what happens basically is the minimum value will be obtained when you have x is basically equal to 3. That's what that tells you. So the minimum value would be square root of 3 minus 1 over square root of 3 squared plus 2, which actually works out to be 3 plus a third when you do it. Right, so that's how you would show that the minimum value is obtained when x is actually the number you want, the minimum value. So in this case, what I just explained, the minimum value was 3. So the answer would be 3 plus a third. So 10 over 3. Right, and like I said, that to me, that's the easiest way to show what the minimum is. It's not easy to show that this thing is an increasing function directly. I suppose you could show it's an increasing function if you use this factorization here. Well, if you use this expression for it. Because if x is greater than y, then you would basically get that this thing is greater than the same expression for y, and it follows then that is increasing. Any questions on that?
Yeah, can you just say that? Actually, no, that wouldn't work.
Yeah, you could see why it might work, but it is not easy to prove it. The only way to prove it is to use this expression.
Right.
Because the reason why it works is because the negative sign in front of the reciprocal will, after you change the sign by taking the reciprocal, it changes it back. So minus signs in front of reciprocals are things that kind of help you preserve the inequality sign. Here, when you take the reciprocal, you don't have a minus sign, so the sign changes. So you can't actually prove it directly using this. But bear in mind, this only works because you need square root of x to be more than this, and that only happens if x is greater than 1. If x was less than 1, then you have, then it doesn't actually work out so nicely. Actually, for x is less than 1, it would be a decreasing function. So the minimum value would be for the maximum value of x you get, if it's less than 1.
If it was between 0 and 1.
Yeah, if it's between 0 and 1, then whatever the maximum value of x you're allowed to take, that would be the minimum value. To show you what I mean by that is, if you look at a graph of x plus 1 over x, you'll see what I'm trying to explain there. Right, so this graph here, x plus 1 over x, that's what it looks like when x is positive. I should probably specify the range a little more. 0 less than x less than 2. Right, so this is easier to see. So the minimum value, well, when x is 1 is actually the absolute minimum here. Right, from 1 onwards, it's an increasing function. The value increases, meaning that the smallest value you take, whatever the minimum bound for x is, that would give you the minimum value. If x was greater than 1.5, then the smallest value of the function would be at x is 1.5. Right, but the problem is when you go in the other direction, when x is less than 1, the upper bound for the value of x gives you the minimum value for the function. So for example, if x was less than 0.5, meaning any value in this range, the minimum value the function takes is when x is equal to 0.5. Right, otherwise it just goes up. And that follows because on this interval is an increasing function, on this interval is a decreasing function. Meaning that when I say decreasing, I mean as the x value increases, the y value decreases. Here, as the x value increases, the y value increases as well. Yep. Right. Okay, so yeah, that's that. Any other questions on that? Why I mentioned that is I wanted to pay attention to the domains given in questions. Sometimes the question might try to trick you and you'll say, well, find the minimum value or something, given x is in a certain range. And if you don't use the fact that x is in the range, you might get a different value from what you're actually supposed to get. So you just need to pay attention to the domain given.
Yeah, sorry, I don't really want to like take up too much time, but for the between 0 and 1, I thought it was weird because if I just make a substitution, x is 1 over y, then y could be it could be a positive real greater than 1, and then it should be an increasing function.
No, but remember, if y is increasing, x is your reciprocal, so x would be decreasing. If you take the reciprocal of an increasing function, you get a decreasing function. So yes, y would be an increasing function. If you take if you make the substitution y over x, where x lies in this interval, then y would now lie in this interval because y is the reciprocal of that.
No, well, I probably shouldn't have used y, but I just want to...
I understand what you mean. So for example, if x was 0.5 and you take your reciprocal of that, if y is 1 over x, then now y becomes 2.
Right.
So it is basically transferring it from this interval to this interval.
Right.
Observations like that are good to make though. Okay, so now we go into means. Oh, is that this? I should have mentioned. I want to at least talk about this one. There is something called the rearrangement inequality, which is very useful to know. So basically, it says this is a simple version of it, or the simplest version you can have. If a is greater than or equal to b and x is greater than or equal to y, then if you take pairwise products of them, basically the maximum what you would get is when you take ax plus by, right? If you pair them up according to the inequality sign. So if a is the biggest, x is the biggest, and you multiply the biggest and you multiply the smallest. So ax plus by is going to be bigger than if you had taken ay plus bx. And this works for any number of things. So for example, if you had another inequality, let's say, I don't want to use weird letters, but let's say P is more than Q, right? P and Q are real numbers. So I'm just using P and Q. So if I also had P is more than Q, then what I would have is, not P is more than Q. If I had A is more than or equal to B more than or equal to C, right? Suppose it was three numbers and three numbers here. X is more than or equal to Y more than or equal to Z, right? It's always two inequality chains, but you could have multiple numbers, more than two. Okay, so assume that we had A greater than or equal to B greater than or equal to C, X greater than or equal to Y greater than or equal to Z. Then again, the maximum would be attained when you take AX plus BY plus C times Z, right? And that would be bigger than any other parents you take. If you take AY plus B, Z plus CX, that would be smaller than if you had taken them when they line up. And that's what the rearrangement inequality basically says. This simple version of it you could prove using, well, just by bringing across and factorizing and those things. For the more complicated ones, it's not as easy. Okay, one of the most fundamental inequalities that you need to know is the AMGM inequality, the arithmetic mean, geometric mean inequality. Now, basically what arithmetic mean means is where you take the average of the numbers. So for example, if you had two numbers, x and y, the arithmetic mean is just x plus y over 2. If you had three numbers, x plus y plus z, then the arithmetic mean would be x plus y plus z over 3, because it's three numbers. All right? Now, geometric mean is similar to that, but instead of adding, you multiply. And instead of dividing by the number of numbers, you take the nth root. So if it's two numbers, you take the square root. If it's three numbers, you take x, y, z and take the cube root. Right? If it was n numbers, you multiply all n and take the nth root, and that gives you the geometric mean. So those you need to know, arithmetic mean and geometric mean. Now what this inequality says is that if x and y are non-negative, then if you take the arithmetic mean, it will always be greater than or equal to the geometric mean. And you would only get equality when x and y are equal. Basically, the terms in the arithmetic mean are equal. Now, this is the simplest version where we only have two terms, x and y. Later on, we'll see the more general version, right? But like I said, if you had three terms, x plus y plus z over 3, that would be greater than or equal to the cube root of x, y, z. And again, you would only have equality if all three are equal, x, y, and z. Be careful though, when we check in for equality, we mean that the terms here are equal, the things that you're adding. So for example, if I had used x and 2y here as the terms, then I would need x to be equal to 2y, not just the variables being equal. Right, the proof of this is straightforward, right? Because this looks like the square root. This looks like something you could square and make something nice out of it. The proof of it is basically if you bring this across on this side and consider what that term is, so I consider what x plus y over 2 minus square root of xy is. If I could show that that thing is, well, non-negative, then that's what I want to show. So if I consider that, right, I could factor out a half first, and I get this. And this looks a little nicer. This is actually square root of x minus square root of y all squared. And since this is a half times something squared, it will always be greater than or equal to 0. And since this is greater than or equal to 0, then that must be greater than or equal to this. Now for equality to occur here, this must actually be 0, which means that square root of x must be square root of y, which means x must be y. Now there are two other means that we're going to meet. One of them is the quadratic mean. Right, the quadratic mean is basically the thing on the left-hand side here. So if you had two numbers, x and y, the quadratic mean is also called the RMS mean. That is another name you might know it as. RMS, meaning the root of the mean of the squares. So what you do is you square the terms, x and y, so x squared and y squared, and you find the average of those. So x squared plus y squared divided by 2 would give you the average, and then you take the square root. Right? So that's why I normally remember it as RMS, the RMS mean, so root of the mean or the average of the squares. And there's an inequality, the QMEM inequality says that the quadratic mean is always greater than or equal to the arithmetic mean. Right? And again, in all of these things, you would have equality if and only if the terms that you use are equal. Right? So the proof for this one is given here. So notice that this thing inside here is really a quarter of this, right? Which you can write as a quarter of, you take one of the x squared, another of the y, one of the y squared, and then you group the other two terms here. What we're going to do is use the AMGM inequality on this, right? This is going to be greater than or equal to, so for the AMGM inequality, basically what you're going to have is, if you consider the AMGM inequality with these two, you'll get x squared plus y squared divided by 2 is more than or equal to the square root of x squared y squared. Now the right hand side of that is just basically xy, because when you take the square root, the squares will cancel. And then you can multiply by the 2 you divided by here, and you'll get x squared plus y squared is greater than or equal to 2xy. Right? So x squared plus y squared is greater than or equal to 2xy. So you could just replace that here and put an inequality sign. Right? And then now this thing is just x plus y all squared. Right? So basically what you have is this is greater than or equal to this, right? So if you take the square root, right? Square root of that now will be greater than or equal to the square root of this, which is just the arithmetic mean. And you're done. Right? So here the only inequality that was introduced was in this step where we use the AMGM inequality. And for that to be equal, you need, well, this is what we used, right? For the AMGM inequality. Now this is not just AMGM, right? You gotta take on this as x minus y squared and factor, expand that and then carry the 2xy on the side, and you'll see this is also true. But for this thing to be equal, you need x to be equal to y, basically. Right, and that is the QMAMGM, the QMAM inequality. There's a third one, the harmonic mean. Well, a third inequality, the GMHM inequality. Right, so we know what the geometric mean is. It's just the nth root of the product of the terms. The harmonic mean is similar to the harmonic. You may have seen the term harmonic series. I think it comes up in physics. You may have seen it elsewhere as well. So the harmonic mean, it's kind of like the reverse of the arithmetic mean. So for the arithmetic mean, you add the terms and then divide by the number of terms. In the harmonic mean, the number of terms is on top, and then you divide by the reciprocal, the sum of the reciprocals. Right? So it's the number of terms above and then divided by 1 over x plus 1 over y plus whatever. That is the harmonic mean. Right, and again, you get equality if and only if x is y. So how you prove this is start with the right-hand side, 2 divided by this, because this is much more complicated than this. So start with the more complicated part, right? Simplify the denominator, and then simplify the whole thing, just multiply above and below by xy. So you get this, right? Now by the AMGM inequality, the denominator is greater than or equal to 2 square root xy. Now, when you're using the AMGM inequality, I should mention, it's written like this, right? But often it's nicer if you take x plus y is greater than or equal to 2. If you put a number on the side, 2 times square root xy, right? Most times it's easier to use that way. So that's what we did here. So put the 2 from the denominator, just multiply across here. Right, so we know this is true, right? So if I take the reciprocal, then 1 over x plus y is less than or equal to 1 over 2 times square root xy, right? Or same, another way you could say it is 1 over 2 times square root of xy is greater than or equal to 1 over x plus y. This comes directly from this. Right, so basically what you get here is that you want to try to make this term using this. So to get that, I need to multiply by 2xy. So I'm going to multiply this entire inequality by 2xy, and this is what I get. Now, this on the right-hand side here is just the same as the harmonic mean. It's just the harmonic mean written in a simplified way. It means that this term is more than or equal to the harmonic mean. But this term actually simplifies, right? The 2 cancels, and then the square root cancels with 1 square root up here. And you'll just get square root of xy. So this actually simplifies to the geometric mean. What this means is that the GM is greater than or equal to the HM. And that's how you would prove it. Now, these proofs, like I said, these inequalities hold for any number of terms, right? But we've only shown them for 2 terms. The reason being, when it's 2 terms, it's easy to prove. When it's more than 2 terms, it's not so easy to prove. So we're not going to actually look at the proofs of those things, but they can be proven if you want to. All right, there are 2 other inequalities I want to mention here. All right, the one with the max and the mean. Oh, actually, here. So if you had 2 positive real numbers, and one thing to note, for the harmonic mean, they have to be positive. They can't be 0 because they can't divide by 0, right? So for all of the other ones, x and y could be non-negative, but for this one, you need positive. Similarly, for this one, you need positive. For this one, they could be non-negative, right? But I included them into one, so I had to say positive. Well, basically what we have is that if you had 2 numbers, x and y, the maximum of those 2 is greater than or equal to the quadratic mean. And the harmonic mean is greater than or equal to the minimum of the 2 of them. Right? When we say max and min, basically what I mean is if x was greater than y, then I would take x as the maximum. Whatever x is the maximum. And if x was greater than y again, then whatever y is would be the minimum. All right, so how do you prove that? To prove that, you have to say, well, without loss of generality, since these things are symmetric in x and y, let's just assume that x is greater than or equal to y. If y was greater than or equal to x, then a similar argument would hold. So if x is greater than or equal to y, it means the maximum value of the 2 of them is x, and the minimum value of the 2 of them is y. Right? So we're going to use that in these things here. Now, if we take the quadratic mean, right? This is the quadratic mean. Now, x is greater than or equal to y. It means that y is less than or equal to x. So if I replace y with x, I get something bigger. Well, bigger than or equal to. So this thing would be less than or equal to this thing. And this thing just simplifies to x, right? Because 2x squared divided by 2 is x squared. And I take the square root, I get x. One thing I want to mention here that it just came to mind that I don't think we talked about before. I know at high school level, some students, even at university level, to be honest, they don't actually understand the difference between the square root symbol and actually taking the square root of a number. The square root symbol is defined as a positive square root. Right? So when you see this like square root of this, it means a positive square root. After you take the square root, you never put plus or minus. The only time you put the plus or minus is when the question says, well, this thing is equal to y squared, what is y? Because if this thing is equal to y squared, then y would be plus or minus. That's where you introduce the plus or minus. But when you're using this symbol is understood to be just plus, which is why, for example, in the quadratic formula, you have to put plus or minus before the square root to indicate that you're taking the positive square root or the negative square root. Right? But this always means positive when you see it without the plus or minus. right? And so yeah, this one is straightforward. And then similarly, if y is less, well, if x is greater than or equal to y, right? Then 1 over x would be less than or equal to 1 over y, which means that 1 over 1 over x is great. Again, the sign changes. 1 is greater than or equal to 1 over 1 over y. So that's the idea you're using here. This thing would be bigger than this thing because this is smaller than this, right? When you decrease the denominator, you actually increase the value of the fraction. All right. Yeah, so this is greater than or equal to this, and then this thing just simplifies to be y. So that proves this one. Now, all four that were previously mentioned can be combined into this single inequality chain. The maximum is greater than or equal to the quadratic mean, greater than or equal to the arithmetic mean, greater than or equal to the geometric mean, again, harmonic mean, and then minimum. Right? A simple way you could remember the order it goes is that, well, maximum is maximum, right? Minimum is minimum. And then in the quadratic mean, forget about the square root on the outside. The power, here you have x squared, you're squaring things. Here is just x, so the power is 1. Here is x to the power of a half. Right? And then here is x to the power. If you think of it, this is the denominator, right? So again, forget up above here. In the denominator, I have x to the power minus a half. So it's like the power of x inside the things decrease each time. Even though really and truly, when you take square root of x squared, you get 1, right? But don't worry about that part of it. Just remember, if you see x squared, that's bigger than if you just see x, which is bigger than if you see square root of x, which is bigger than if you see 1 over x. I find this a useful way to remember it. Right, like I said, this is only for 2 variables. You can have any number of real numbers. So again, the maximum would be the biggest, then the quadratic mean would be this thing, the arithmetic mean would be this, the geometric mean is the nth root, right? And then the harmonic mean. Okay, so this is some exercise questions for you to try. Now you could use AMGM in creative ways. So for example, in this one, right, I have x cubed, y cubed, and 1. I could take this as a, b, and c, and just take the AMGM of these 3 terms together. And I will get the 3, and then I'll get the cube root of x cubed, y cubed, and 1. The product of those, which would work out nicely. So this is a straightforward one. This one is not as straightforward. What you have to do is take the AMGM of each individual bracket. So take the AMGM of this, AMGM of that, AMGM of that, and then multiply all 3 together to get what you want. This one is similar. You're gonna have to split it up first. So what you should do is compare what you want to show, right? I have x and square root of y, square root of z. I could get this if I take square root of xy and multiply it by square root of yz, xz. So what I'm gonna do is split these up into a half xy, a half xy, a half yz, a half yz, and a half xz, a half xz, and then combine pairs, similar to above here, to get what I want across here. So that's what you should do there. This one you're gonna have to be more creative. All right, so you're gonna have to, again, split things up. You're gonna have to take a half x squared and a half y squared and a half, and then a half x squared and a half y squared, and see if that helps. All right, and then these 3, so once you get an idea of ways you could be creative with the AMGM, then you could try to use some of these. All right, this one down here has squares, so you might start thinking about QM. But it isn't divided by 2 though, so you have to, again, try to figure out what to do with that. Okay, we'll pause here for a little bit and then come back and talk about the Cauchy-Schwarz inequality. There are actually many different inequalities that you could look at. There's Jensen's inequality that requires some calculus. There is, I mentioned, rearrangement inequality. You could look at the general version of that. There are many other different things like Chebyshev inequality, Minkowski inequality, Holder inequality. Knowing all of those things can be helpful, but it's not required that you do know them. Although for somebody more advanced IMO problems, if you know them, you're kind of able to solve the question a lot more efficiently than if you didn't. Sometimes you might even see how to solve it without those. Right, but this is really advanced one we look at, the Cauchy-Schwarz. So we'll take a break and then start back with this.